And I like think about this, right? How good friends we all are. I'm very happy last night then, of course. And I think much I love the NoSQL space. So I sit down there, it's like, there's a bunch of things that people haven't said already. And so I start, I fire up my old open office and I start adding slides. It's like, someone should say this and this. Hey, and this and this and this. And 2 hours later, I get a bit tired, so I go to bed. And I wake up slightly less happy this morning. And I look through my deck and it's like 40 new slides. I'm like, holy shit, who the fuck added this, right? So I'm like, I got to delete this shit, right? But then I figure I need breakfast first. So I go down and I have breakfast and I have coffee. And I actually, hey, coffee. So I wake up after a while. And I go back up to my room and it's like, hey, these slides are not too bad. I drink some more coffee and it's like the caffeine kicks in. So I keep adding more slides. So where we are right now, I talked to Brad and Chris before, and we decided to cancel lunch. There's just going to be me talking for 3 hours now about maths and graph theory and things like that. Is that cool with everyone? Yeah. Fantastic, right? So hi, I'm Emil. I work with Neo Technology, which is the commercial backer of the Neo4j open source graph database project. And before we get started, just some ground rules for this talk. I do not want your undivided attention. I realize that we can't be on Twitter right now, but if the network starts to work, feel free to tweet about this, give me feedback, send me mail. The only thing I ask is that you use this hashtag. I'm Emil Ephraim on there, and you can send me mail as well. So this is the plan, right? I'm going to talk about 4 things, and then finally there's food. I'm going to talk about 4 trends of why I think that right now, why 2009 is the year when NoSQL space happened. I'm going to give a brief overview, which I'm surprised to see that no one has done so far. And then I'm going to zoom in on my stuff, the graph databases, and convince you that the only true way is the way of the graph. And then I'm going to wrap up after that. I'm going to try to keep a fairly rapid pace. Interrupt me if I'm unclear on something. If you have more thoughtful comments, please keep them towards the end so that everyone we can see how I do on time. So 4 trends why I think NoSQL space is happening right now. The first one is about dataset size. And you can see that I've been out raising money because this is actually a quote from an analyst firm. But I can assure you that this is the only analyst quote that I'm going to use. This is a report that came out 2 years ago. It's a pretty fascinating report. They try to estimate the amount of unique new digital information being created every year. And so, for example, a text message would be, unique new information. A digital photo would be something. It's human-generated new information. And they estimated to 40 exabytes. So that's 1 exabyte is 10 to the power of 18. So it's quite a lot. The amazing thing, though, is not that number. It's the growth rate. So they predict an exponential growth rate. So next year, there's going to be like 1,000 exabytes of digital, new, unique information being created. And the funny thing about exponential growth, as you guys probably know, is that next year, there's going to be more new information created than all the previous years in history combined. And the same thing will be true of 2011 and 2012. There's a huge explosion now in data set size, so that's trend 1. Trend 2 is that of connectedness. And let's say that we have a time axis here, decades, and sort of a fluffy concept of information connectivity. And we map technologies over the past X amount of years. We see that we have text documents down here, completely isolated information structures, not any connectivity whatsoever. Hypertext adds 1 level of connectivity to documents. You can click and you can traverse to other documents. On this y-axis. That's why everyone was waving. I was like, this is going really well. All right. Okay, can you hear me? So I then typically take blogs as an example. Blogs have a trackback functionality. So when I write something about the NoSQL East conference, my blog will ping the NoSQL East blog. that blog can visualize that ping as a link, but you can clearly say that the semantics of that is we're in a conversation. You can write software that spiders the web and finds out who's talking to whom, not just who's linking to whom. So fairly arbitrarily chosen technologies, but I think the trend is clear. Over time, information has become more and more connected, so that's trend 2. Trend 3 is that of semi-structured. So semi-structured information is information which has a few mandatory attributes and many optional attributes. And the problem with them and tables is that they lead to so-called sparse tables, right? You have a lot of holes in your tables. And the whole Web 2.0 trend where you can add tags dynamically has just accelerated this growth of semi-structured information. So that's trend 3. And quick aside, if we then take trend 2 and 3, look at connectivity of information, how connected is information, and degree of semi-structure, and we lump that together as data complexity. How complex is data? And we look at the relational dudes. OK, they're not up there. The relational dudes, the performance curve for them looks like this. And remember, we haven't even talked about volume here, right? We're only talking about complexity. And this is due to the fact of sparse tables is the one thing. And the other thing is joins, because every hop in a connected network is a join in a relational database. So for example, the cellular list applications, extremely structured applications, very tabular. They have kick-ass performance for that. But even the average web application of today deals with substantially more complex information and has substantially less performance. There are a number of industries or verticals today or applications where they don't even try to use a relational database. We all know about this. The example that I typically say is that of Facebook, which has hundreds of 1 terabyte of RAM machines that they use to traverse their graph in order to generate the stuff that they show up on the every profile view. And that's a fine enough solution if you're Facebook. If you have Facebook's cache, you've solved the problem. But to me, that's an infrastructure bug, right? We have infrastructure which is optimized for calculating average salary on very well-structured data, whereas the common queries today, the important queries, the real-time queries, they suck at. So trend 4. There's been this shift in architecture, and we covered this yesterday, before the happy yesterday. We talked about this at the taco place, where in the 80s and the 90s, we sort of used the database as our shared data integration hub. All our applications connected to it. We had the main applications, we had reporting, we had Excel connecting to the one shared, typically Oracle instance, the enterprise Oracle instance. And we used that as a way of basically sharing mutable state. The problem with that, of course, is that this thing becomes extremely fragile. I mean, I guess depending on the age of how old as a professional programmer you are, but we've all been there, right? We sit down and we want to change something in our application, and either the DBA completely forbids us for doing it, or the chief architect won't allow us to do it because it'll break other applications. And I was there and I hated that, right? And then when I was the chief architect, I was there telling all these kids that, come on, you can't change this because something would break. We just didn't know what, but something would break. And so that's a horrible, the database is not good as an integration bus, right? So that's what we've learned. And I think the Guild presentation, Gary's presentation yesterday, showed a really nice evolution sort of its older style architecture into more modern style, where each and every application or service got their own backend. And they spoke a service domain-oriented language or protocol over the wire with one another. And that, of course, means that the entire ecosystem is less tied into the one shared Oracle instance, typically, which means that obviously the cost for switching out that is way less. So suddenly we can start getting these databases which are sometimes better for the typical use cases of one of the specific applications. We can actually swap in a separate database. So those are my four trends of why I think that now is really the year of NoSQL. Why did this happen right now? So NoSQL overview, really quickly. How do I look at the NoSQL space? Well, OK, so first off, the name, right? So in my view, NoSQL is not never SQL. NoSQL is not no to SQL. NoSQL isn't even something about Chris's dog, right? There's no hate in that, right? NoSQL is very simple to me. NoSQL means not only SQL, as in the backends of the future, there will be not only SQL databases, but also other databases. Not only SQL. I think it's a fantastic name. So if there's one takeaway, right, this is it. This is it. If you guys follow me on Twitter, this is like half my tweets. Half my tweets are, NoSQL is not never SQL, it's not only SQL. I mean, Kevin, you guys can probably optimize that, put that in Twitter, that some binary compression on that one tweet because I say it so often. This is a young space, but I think that we, at this point, we can sort of see 4 emerging categories. And I'm going to quickly go through each and every one. So we have the key value stores, and they're based all off of the Dynamo paper in some senses. And they have a data model, which is a collection of key value pairs, very simple key value thing, right? And examples here are Dynamite and Voldemort and Tokyo and so on. We've had a number of these presentations. This is clearly the most popular category. As Jonathan likes to point out to people, please don't start another key value store clone project. And I think that's a good point. The second category is the big table clones, and they're all based off of the big table paper from Google. And they have a slightly more sophisticated data model. It's a big table, but it has this thing about column families that we know, and that's how they can represent semi-structured information. So theoretically, each and every row can have an individual schema, theoretically at least. And there are 2 that I know, 2 implementations today. There's HBase off of the Hadoop project, and there's Hypertable. And it's a good old Java versus C++ fight, is, I guess, the core difference between the 2 of them. Then there's the document databases. And Couch is the main guy here, right? And MongoDB is the other implementation. And basically they're all inspired by Lotus Notes, at least in spirit. And what they have is that they have a collection of key value pairs, which they call documents. And finally, the graph databases, right? Inspired by Euler and graph theory. And what the graph databases have, they have nodes and relationships and arbitrary key value pairs that can attach to both nodes and relationships. Examples here, Allegro Graph, VertexDB, and obviously we're Neo4j, which is my secret agenda to convince you all to use Neo4j. So the interesting thing about these 4 categories is that they're sort of different in their focus. And I find it very useful to look at it on 2 axes. They're all focused on scaling, but they're scaling to complexity, and they're scaling to size. So how well do you deal with complex data, and how well do you deal with volume? So if we map these 4 categories here, we have the key value stores. They're extremely good for scaling size. Extremely good. They have, however, they have a very poor data model, a very simple data model, which puts them all the way down here. It's very complex to push in complex data in them. The gain, of course, is that you have very little data which has coupling in it, which means that it's very easy to partition it and scale horizontally. And scaling to sizes, as we all know, all about scaling horizontally. So then we have the big table clones. A slightly more sophisticated data model can fit this semi-structured thing that we talked about. Scales slightly less to size. We have the document databases. They have a higher abstraction than these guys in terms of complexity, but can scale to size as well as the key value stores of the big table one. And all the way to the right are the graph databases. This is my subjective view, obviously, but I think it maps pretty well. The interesting thing, of course, for me is that scaling to size is awesome, right? It's extremely sexy. It's cool to talk about petabytes, but the reality of my world is that I'd say that 90% of the use cases are here or probably actually down here. Sure, Google is clearly up there, but there are only so many petabyte installations out there today. So the interesting thing about these data models is that they're all isomorphic. and so mesomorphic is just a fancy way of saying that you can losslessly transform data in one model to the other one, which means that you can basically represent data in each and every one of these models. The question is, which data model fits best? It's sort of the same as with programming languages, right? As long as you have a Turing-complete programming language, you can theoretically write any piece of software. But which programming language is best suited for that type of data? And I think that's the world where we're going, this polyglot persistence world, where it's all about trying to figure out which data set, which database is the best fit for my data set. So that's my crash course in the NoSQL space. Now, graph databases. So am I going too fast? Am I going too slow? So graph databases, we have three core abstractions. We have nodes, we have relationships between nodes, typed relationships between nodes, and we have arbitrary key value pairs on both of them. Those are the three core abstractions that you use to model your entire, all your domains with, your information with. And so if we look at an example, let's say that we wanted to model the social network from the Matrix movies. Should come as no surprise that I like the Matrix movies. Neo technology, right? The first thing that we want to do is we want to identify the entities in the social network. And the entities are people, typically. In this case, we have someone called Thomas Anderson. And the properties of him are represented as key value pairs that we attach to the node. The node only has one mandatory property, which is the ID, number one, and that's assigned by the database. After that, we identify the other entities, and in particular, we identify how do they relate to one another. So in this case, we have Morpheus and Trinity there, and they know one another. So we have relationships of a type called knows. This is actually a poor example in the sense that knows is typically a symmetric thing. Knows of, I guess, would be better if it's directed, but you get the point. You can see that we can represent semi-structured information. We have three properties here, we have two here, and we have one here. In this domain, it seems like the only mandatory property is name other than ID, but that's a convention. That's nothing that the database enforces, so that's completely semi-structured. You keep adding things, right? The joke, of course, I'm not sure if you guys remember the Matrix mythology. I'm sure you do. Of course, the mythology was that the bad guys were actually programs. And the most evil thing that I came up with was C++. They're coded in C++, right? And here we can see that they were coded by this cool architect dude that appeared in the second movie. And we have a new type of relationship there called coded by. Turns out that the types of relationships are really important. I think a lot of what the semantics of a domain is actually encoded in how things are related to one another, not just that they are related to one another. Josh, go.
Do the relationships between nodes have properties too?
Yes. Sorry, good point. I forgot to add that. Yeah, so basically you can add an arbitrary amount of key value pairs, also known as properties, right, onto the relationships. So for example, here we try to model that, Thomas Anderson and Trinity have known one another for 3 days. So the values that are valid values on properties are anything that is a primitive in the JVM. Go.
Are those relationships bidirectional or unidirectional?
So these are directed, but you can express both. All right, so I'm legacy enough to think that Java and object-oriented languages are good. So I'm going to give examples in Java. We have bindings to pretty much anything on the JVM. So if you want to use Python or JRuby or Clojure or anything like that. But I'm uncool enough to use Java. So I think the API is fairly straightforward. We have a Neo service. We execute create node on that. We get the node back. And then we basically have a hash table interface. Set property, we pass in key values in there. We have a method on the node called create relationship to, where we pass in the other node and the relationship type. A really important thing is that everything when you work, every operation when you work against Neo4j has to be embedded in a transaction. We love transactions. We think transactions are a fundament of databases. It has been forever, and it will be in the future. We think you should start with a transactional core, and then after that, you can add eventual consistency and those kinds of softer types of transactionality if required. But you should start with a really transactional core. So the relationship types. In our API, this is code straight out of our API implementation. A relationship type, as you can see, is just anything which has a name, which means that you can define your own relationship types, really simply. This means that you can dynamically detect a new condition, and as long as you have a name for it, just instantiate one of these guys, pass it into the database server, and it's just going to say, hey, OK, cool, this is a new one. I'm dynamically going to create it. So that's awesome for very dynamic applications. Most applications, however, aren't that dynamic. When you sit down and you build something like an e-commerce site, you actually know beforehand how things are related to one another. And then it's really neat to be able to get a compiler to help you out if you start working with a relationship that actually doesn't exist. So that's why we integrate with the Java enum pretty well. Basically, I'm not sure how into Java you are, but the enum, the Java compiler actually synthesizes a name method on each and every enum implementation, which obviously implements that name over there. So it's really easy to just declare an enum, make it implement relationship type, then just stack all your types in there. And from there on, you have type safety. So the compiler will help you. So a step back from the code. So one of the things that we talk about is whiteboard friendliness. And that's the observation that when we interact with clients, one of the first things that we do is that we stand in front of a whiteboard and we try to figure out the domain with them. And they're not computer geeks, right? They're domain experts in pensions or something like that. And when they draw stuff on the whiteboard, it's very seldomly tables. It's typically they start off with something like, yeah, this is a customer, and the customer has a cart, and the cart has a number of products. Products belong to categories. Categories can be shared and whatnot. So that's typically a graph. And it's very interesting for us to see that 6 months down the line, when we've taken that project and we put it in production, and we take the initial whiteboard drafts, brainstorm drafts, we typically see a one-to-one mapping from these initial brainstorming sessions that we had on the whiteboard to the graph that we have in production. And I think that the fact that we have this whiteboard friendliness, that we map really well to the concepts of the domain, I think that's a very powerful thing in terms of programmer productivity. I think that the cognitive model of the programmer is that we don't think naturally in tables. I don't think we do. Maybe if we model salary list, because then the natural representation of that domain is a table. But most domains aren't tables. Domains in our head as programmers are this. And it's really powerful to be able to have a one-to-one mapping of that cognitive model to the data in the graph. OK, I'm going to skip that. That was a really funny thing that you guys miss out on. But actually, yeah. But I'm going to cut through that. So that's how you build up stuff in the graph. That's the representation part. Then how do you get stuff out? Well, then you use the traversal framework. So let's say, going back to our social network here, let's say that we wanted to find all the friends of Thomas Anderson. Conceptually, what we want to do then is that we want to start traverse from node number 1. We want to go breadth first along the nose relationship types. We're going to breadth first all the way. We want to go breadth first because we want his closest friends first. I'm going to traverse all the way through the graph until you can't find any more nodes. So that's his sort of friends of friends graph. And how you express that, and this is the peak of the complexity of this presentation. So if there's one time you're going to pay attention, now should be it, right? Basically, the way you do that is that you work with the traversal framework. And the traversal framework has iterators called traversers. So this traverser implementation here is actually a Java iterator. It's actually an iterable, but let's call it an iterator. And we get that back by executing a factory method on the node called traverse. And that factory method does nothing but return a traverser which is positioned in the graph. So it doesn't start any traversals or anything like that. It's a completely lazy evaluation. But it's configured by a number of parameters. And in this case, it's breadth first, because we said that we wanted his closest friends first. It's the node relationship types in the outgoing direction. And then there are two evaluator methods, which are used by the traversal framework at the specific instances in the traversal. The first one is the stop evaluator. And that guy is evaluated right before the traversal framework would have made the next hop, so to speak. And it's going to answer the question, should I stop traversing now or not? And now we're going to say end of graph because we wanted the traversal framework to just traverse as long as it can find friends. Another stop evaluator would be something like depth limit to depth limit 1 or 2. And the second evaluator is a returnable evaluator. And this guy, on each and every node that the traversal framework visits, it's going to say, should I return this node? Is this node part of the result set? In this case, we want to return all the nodes except for the node that we started on because we wanted his friends, not Mr. Thomas Anderson himself. So that thing only positions the traverser. It doesn't actually start any traversal. That happens here in this. This is the for each loop for Java 5. And basically just iterates through this thing until the end. It gets a node back, prints out a property, a name property from that node. It gets some context information from this current position thing, which contains some candy, like current depth, how many nodes have I returned, what was the last relationship that I traversed, good stuff like that. So looking at this, what's going to happen is we're going to start over here, and the first thing that the traversal framework will do is that it's going to invoke this guy, the returnable evaluator. I'm positioned on a node, now should I return it? And in this case, it's going to say, hey, dude, this is the start node. No, let's not return it. So then after that, it's going to invoke the stop evaluator and say, OK, should I keep traversing? And this is just going to say, yeah, always keep traversing, just as long as you can. All right, cool. So the next thing it does is that it grabs all the relationships from the node, actually the first relationship from the node that matches this filter. And you can stack. This is a var arg, so you can add however many relationship types and directions here that you like. It's going to get one of those guys back. It's actually non-deterministic. It's undefined which one. For optimization reasons, we want to be able to shuffle them around on disk. So you could get either that one or that one. But let's say that we got the one that leads to 7. So it's going to go to 7. The first thing it's going to do there, it's going to invoke the returnable evaluator. Should I return this thing? It's going to say, yeah, because it's not the start node. That one will return. It's going to ask the stop evaluator, no, and it's going to keep traversing. Traversing all the way until it gets to 13, at which point the stop evaluator will still say, yeah, keep traversing, but it won't find any relationships that match the filters that we have of nodes and outgoing. So in this case, the output would be like this. It actually could switch around Morpheus and Trinity, as I talked about.
So,
go.
so if you go the route of where it's going, you start going Morpheus first, and then it gets to Trinity. When it gets to the point about where it's processing the second outgoing link from number 1, does it say I've already seen this node?
Yeah, it's going to detect that. So the traversal framework we have right now is actually written. Oh, so the question was, do we detect cycles is basically the question. Do we make sure that we don't visit the same nodes twice? And the answer is yes, we do. The traversal framework is written on top of the core representation API, so there's nothing special about it. And we try to find this sort of 80-20 thing, where it makes sense for 80% of the applications. The fact that we do cycle detection is what you want for most cases, but sometimes you don't. It certainly has a memory overhead associated with it. It also means that you won't necessarily visit all nodes. Visit all relationships. There might be 2 paths to a node, and you're certain to get to that node, but you might not visit all the relationships. So if you have an algorithm that depends on calculating something based on the relationships, then you shouldn't use the standard representation API. And by that, I mean node.get relationships and stuff like that, right? So when I do this, typically on stage, we're actually 2 guys, and we have sort of this role play going where I'm the customer, and my CTO actually sits there and writes the code. And mid-air, of course, I change the problem. I change the domain. I add a new feature request because we all know that customers do that all the time, right? And so the thing that I add then is that I want to be able to model love. You know, we want to be able to model that Trinity is in love with Neo or with Mr. Anderson. And which is a pretty cool thing because, you know, it's less cool now that I just talk about it. But when he actually sits there and writes the code, you don't need to restart the server. You don't need to do anything. You can just add this new loves relationship type on the fly and create a relationship, and off you go. But let's say then that we wanted to have a new type of traversal, which looks through our social graph, our friend of friends, so basically the same traversal as before, but only return people that are in love. How would you do that? So conceptually, it's the same traversal, but with another returnable evaluator. So the way that works is that basically it's the same thing here, right? But instead of a standard returnable evaluator, the last time it was all but start node, right? Instead of that, we actually pass in our custom implementation of that. And obviously, this is a lot better represented in languages that support closures or blocks and things like that. But setting aside sort of the syntactic sugar that Java unfortunately adds here, this is just basically a one-liner. If this guy returns true, we're going to return the node. The node is going to be part of the result set. If not, not. And that's basically the same code. So you know, going here, we're going to go to 7. We're going to go, and 7 is going to invoke the returnable evaluator, which won't find any outgoing loves relationships. When we go down to 2, it will, and 2 is the thing that's going to be returned. All right, so that's sort of the fundamental way of how you work with the database. The question then is, how do you write a domain on top of this? Really quickly, let's say that we have a person. And the standard Java sort of pattern is to have a person interface and then have an implementation of that as a class. Because we like to type things in Java, right? So the interesting thing, what the typical pattern then with the normal database is that you would have a load store pattern. You would read it from the database all the way over there, read it into memory. You would operate on it, and then it would write it back. And we're an embedded database, and we're a graph database. So there's no need for that whole load store thing, which is completely unnecessary and leads to a bunch of problems, which we can get into if we have time. But the way you do it is that you actually, your person implementation wraps a node. And it gets passed in under construction. And let's say that we have a name on this person. What it does, it just delegates to the node, gets a property called name from the node, and returns that out as a string. So it turns out that rather than just having private string and using a load from the database and read it in there, you actually just delegate to the graph database, which means that all state in your application will be held by a database. And the database is really kick-ass at doing things like transactionality. And transactionality is really good for making sure that you can act as if you're completely alone and single-threaded in your application, even though there's a bunch of other threads going on at the same time. This is called software transactional memory, and it's a really neat way, one of the many approaches of dealing with this sort of multi-core parallel world that we're living in. Same, obviously, you know, for set name. Yeah, we have a bunch of frameworks that help you with this, but let's not get into that. All right, so we're disk-based. Sometimes when I give this presentation, people ask me, cool, awesome, cute API, ML, that's really nice, but what about persistence? I want to store shit. You know, we're a database, you know, we store stuff. So completely transactional. We interface with the Java Transaction API. We do two-phase commits if you want to use them. We like two-phase commits. We think they're an awesome hammer for a lot of jobs. They're a hammer that is more applicable in terms of volume to many more jobs than base is, for example. Transaction recovery, real transaction recovery. We've been running since 2003 in production. And we've had a number of cases when hardware has blown out and what processes have been killed, and the transaction recovery process really works. Deadlock detection, we have MVCC, multi-version concurrency control, a lot of good things related to transactions. We scale up on a single box, which basically means that when we start adding more cores, we will gracefully improve performance. When we add more data, we will have the same performance characteristics as before. We scale to several billions of nodes. not hundreds of billions, but several single-digit billions on single machine hardware. After that, you're going to have to do some form of sharding. And yeah, we started working on this technology in 2000. This implementation, this code lines, we started in 2002, put it in production in 2003. So it's been running in real 24/7 production since, for 6 years, something like that now. So it's fairly robust in terms of the underlying technology. It's not super perfect when it comes to documentation and things like that. And it's certainly not perfect in terms of ease of use. But the underlying technology is rock solid. So, performance example. Let's say that we have a social network of 1,000 people, and every person knows 50 other persons. What we want to do, we want to grab 2 nodes out of random, and we want to figure out, are these guys related somehow? And we want to limit it to depth 4, because otherwise we're going to traverse, sort of 6 degrees of Kevin Bacon. Everyone knows everyone within 6 degrees, right? We implemented this using 2 backends, MySQL and Neo4j. And we wanted to eliminate Disc.io because we wanted the overhead of the actual model. And in MySQL, on this laptop, though not with the latest Ubuntu apparently, but with this laptop, it's a 2,000 millisecond operation. This boils down to 2 tables, right? One person table and one friends table. The person table will have 1,000 rows, and the friends table will have 25,000 rows. So it's at least an 8-way join. I think it's actually more, if I remember correctly, because it's an 8-way join to cover for the 4 depth, but then it's a variable length path, right? You need to be able to find even if they're 1 hop away. So it's a fairly complex thing. And we do it in 2 milliseconds, right? Which is good. This is the difference between being able to use it in production or not, right? You can have this as part of generating a profile page, whereas the first one you can't. But it's also, this is what we're supposed to be good at. This is traversing graphs, right? So we upped the ante, being the hardworking, IKEA-loving Swedes that we are. We upped the ante. So we added 1 million nodes, and still the same pattern, so 50 average relationships. So that's 25 million relationships running on this laptop. And we're still at 2 milliseconds for that. So graph traversals, we're good at that, is the conclusion. That's what we're good at. It's easy to show on slides, right? So I pull in Twitter as a backup. And so someone here tried it out and said that SQL Server did it in 45 minutes and did it 2 seconds in Neo4j. Another guy said that 40 megs per second write speeds out of Neo4j and Lucene. So it's not just slideware performance. I can tell you that. OK, so then what are the pros and cons of this compared to a relational database? Probably for this audience, I should make a pros and cons compared to NoSQL. But sorry, I don't have that prepared. But compared to the relational guys, it's no OR impedance mismatch, right? There's some ON or OG, object node or object graph mismatch, but it's much less mismatch. It's very easy to evolve the schemas. We don't have any schemas, right? We're schema-free. So it's easy to sort of organically grow the graph as business requirements change. We can represent semi-structured information. We talked about that. And we have pretty spectacular performance when it comes to traversing graphs and networks. The huge drawback is this, right? There's a lot less tool support for this than for any relational database out there. Basically, we as an industry, we worked for 35 years on providing tools for relational databases. So, we're way behind on that, obviously. And as of today, there are a few other implementations, graph database implementations. But I think I can objectively say that we're the best one, honestly. So if you really go in there and you push it to the edges, you're going to be locked into us. Then we're the only implementation that can handle it at this point. So that's clearly a drawback, right? And this one is actually not true. I'm not sure if you guys thought about that, but the query API, the traversal API, is programmatic, which typically is not well suited for ad hoc queries, right? because you would have to sit down and actually compile classes and shit like that. But we've actually now integrated Sparkle support, which is this semantic web query language, which is completely graph-oriented. It looks a lot like SQL, but it's graph-oriented. And so now we can use, you can use ad hoc reporting for that kind of stuff. Right, I'm going to breeze through these guys. I think we actually covered all of them. Right, so we're a small, tiny, tiny little jar file. We're less than 500K. We have one dependency, which is the JTA, the Java Transaction APIs. We're big believers in sort of a component-oriented architectures. So we've opted to add all the richness on top of that as different components, so you can sort of assemble your own configuration. We have a number of things there, like pattern matching, define patterns in the graph. We have an optional meta model, so you can say that these nodes are person nodes, and they must have a name and an age. They can't forbid you, so you can always add more than that. But that's something that you can say. And a bunch of other things. Components.neo4j.org, if the network works. You guys seem to still be listening, so I guess the network isn't working yet. Oh, it is? OK. So thanks. We have a bunch of bindings. Bindings to Python, Jython, to Ruby, to Clojure, to Scala. And I'm hoping to get even more. There's been a lot of talk about .NET bindings. No one has really stepped up yet. All of these have been provided by the community, which I think is pretty awesome. As of 2 or 3 weeks ago, something like that, someone wrote a Grails plugin, which I think is pretty cool. So Grails is this Java platform, sort of, it's like Rails, but running on the Java platform. Someone just contributed a Neo4j plugin to Grails, which I think is really cool. I actually sat down last week or something like that, and just, I know you guys can't see this, but it's like 8 quick steps. You know, you from just having Grails installed, not even having Neo4j installed. You know, you go Grails install plugin Neo4j, you create a couple of classes. This is like, you know, what, 10 lines of code to define books and authors. And then you have an application up there. You can start adding books and authors, and it's directly persisted in the graph. This is a dump from NeoClipse, which is our plugin to Eclipse for visualizing the graph, of just adding a couple of books. And you see that, you know, this book is authored by this guy, and it's an instance here, and it's related, and one another. I think that's a pretty cool thing. So scale out. Where we are there today is that as of today, there's no built-in replication. And that's what we're working on right now. We're about to roll that out. So basically, today, however, we have a number of installations where they actually do replicate the data. And they do that mainly by using the online backup. We have an online backup functionality, so we can provide snapshot backups. And you can obviously use that with very low increments to get almost, well, not synchronous, but a very short delta replication in there. Before the end of the year, we're going to roll out the first release of high availability. And we're not 100% on that, but we think the configuration will be something like this. It's going to be very MySQL style, which isn't cool, but which is good enough for 99% of the people out there. And that's what we're going to start with, right? Except that all the instances can write. So the problem with MySQL, master-slave replication, as you guys probably know, is that you need to write to the single master. We're an embedded database, so typically the way you would use this is that you would have the application stack on each and every machine. And then it makes no sense to have that these stacks can't write, because then you would have to have different versions of the application running on each and every slave. So the way it works is that the slaves can open synchronous, we're talking two-phase commits here, synchronous write operations that will talk to the master and, you know, have very strict consistency and locking there. And then it will be asynchronously propagated to the slaves. So that's what we're rolling out. And this takes you to billions of entities. It takes you to higher read load, obviously, than just a single instance. But not 100 billion. We have a couple of customers now that need to get to 100 billions within a few years. So that's clearly where we need to go. Hundreds of billions, that's the data set which is very easy to say, but it's harder to do, right? Hundreds of billions in a completely random graph. That's very, very difficult to handle in a scale-out manner because it's so completely interconnected and dynamic. Today, you can use sharding, obviously, just as you can use sharding with MySQL or anything else, but the onus is of you as the client to provide the sharding algorithm. But if you know that this part of the graph will never be connected to that part of the graph, then you can just put it there. Now he starts to wave at me, so I guess I should round up. And what we're working on is the next step for us then is Neo4j 2.0, which is automatic sharding, using basically clustering algorithms to figure out that this graph should belong on one server because this part of the graph has very few connections to this other part of the graph because you obviously want to minimize the network round trips of doing traversals. I'm breezing through this now because they keep glaring at me. There are a number of other implementations. You can talk to me about them. Conclusion, or almost conclusion, is graphs are good. Neo4j is good. It's out there. We use the AGPL, which basically means if you're writing open source software, then we're open source. If you're writing proprietary software, then you must buy a commercial license. However, if you are below 1 million primitives, so 1 million nodes or relationships, it's still free. So then you can use it for whatever use cases. And here are the URLs. Really quickly, this conference has been great. I've loved this conference. However, there's been way too much agreement. There's way too much agreement. I'm from Sweden, right? Pseudo-socialist country. We're all cuddly and cozy and agree with one another all the time. I'm in America now. This is supposed to be like cutthroat capitalism and disagreements here. So in order to spice things up, I added some party pooper slides. So poop 1, key value stores. I think key value stores are awesome if you're Google or if you're one of the 10 installations in the world that need them. Any other time that you want to use the key value stores if you hate programmer productivity. Imagine writing, what if you wrote a complex piece of software and the only thing that you had available to yourself was a hash table. No local variable, no linked list, no objects, no structs, nothing like that. You put everything for int I, no I. For int get something from the global hash table. That's how working with the key value store is like. What the hell? Come on, guys. We need something which is a lot better than that. That's poop 1. Poop 2. OK, so in a nutsack architecture, i.e. an architecture like this, the only thing that makes sense is to have an embedded database. Why would we put these guys on separate machines? Just because that's the way it evolved in the 80s when TCP/IP came along and we stuck a socket on relational databases. The only thing that makes sense here is to put them on the same machine, have locality of data, have local querying. Why is everyone writing standalone databases these days? Makes no sense in a modern architecture. That's poop 2. So poop 3. We've already said that exposing your data model on the wire is bad. I mean, we're slowly getting out of that right now, the hell of having everything integrated towards a single data model. And it's bad when it's SQL over sockets, but just because we had a few fancy buzzwords and acronyms doesn't make it less bad. Just because it's JSON over REST doesn't make it OK for all your application to speak to a single database instance and a single database model. Don't let fancy acronyms blind your way towards a real, sound, solid architecture. Poop 4. In-memory database? What? I mean, database is supposed to be on disk. I mean, come on, seriously. That's like saying, a loop-back-only web server. It's a web server. It serves web pages really fast, but only on the loop-back interface. I mean, come on. If it's, embrace what you are. If you're in memory, you're a cache. If you asynchronously spill stuff over on, to disk, then you're a cache which asynchronously spills stuff over on disk. It's that simple. But OK, so that was sort of tongue-in-cheek, half serious, half not serious. What I really think is that we are moving towards sort of this polyglot persistence world. I really feel that 5 years down the line, the program of the future will use SQL databases as well as a number of NoSQL databases, not only SQL, remember? I'm not sure how read up you guys are in relational database history, but where we are now reminds us me a lot of relational databases in the 80s. In the early 80s, there were no relational databases companies out there. But it turns out that all the computer manufacturers, this was in the 80s, so there were no software companies. Well, they were hardware and software companies, right? Computer companies. And all those guys had internal implementation over the relational database thing. And then Oracle came around as a software company, started selling a relational database. And there was this Cambrian explosion of a huge number of relational databases. And there was a market suddenly, a relational database market. And at the end of the 80s, 5 years later, there was a $1 billion market. And that, to me, is really where we are now. We're clearly in the Cambrian explosion, as the first keynote speaker said. We're at the Cambrian explosion of that. A couple of years back, there were a bunch of NoSQL databases internally at Facebook, at weird Swedish companies, at all these places, right? But now we're in the Cambrian explosion part of that, and I really feel that 5 years down the line, we're going to look back at this and say that 2009 was a 9 of the NoSQL databases. And there's like 200 people of us now, right? And we're defining this field, which I feel is fucking awesome. And 5 years down the line, we're going to sit there and say that, hey, what we defined back then in 2009 is what all these people have used to build all these amazing new technologies. And that, to me, honestly, that blows my mind. So I want to wrap up with a quote by a guy called Julian Brown. So Julian Brown is the guy that I sometimes describe as, he's the most underfollowed of the guys that I follow on Twitter. He's written a bunch of cool things about scalability mainly. His treatment of the CAP theorem, I think, is the best out there today. And the quote he said this quote a while back, which was, even after arguments about ACID and scale and CAP, it's just more human and more agile to be graph-based. So I want to urge you guys to, when you leave this fantastic conference and go out in the real world, to be human, to be agile, to be graph-based. Thank you very much. Okay, you feel them. Okay, go, yeah.
Can you talk about the actual physical storage of the database, and a little bit, is there any kind of referential integrity what we have in the relational world with the relationships?
Right, exactly, good question. So I actually removed those slides because we're supposed to not talk too much about the internals. So basically what we have, so the question was, talk a bit about the internal, the physical storage, and what about referential integrity, the equivalent of referential integrity in the graph. And in terms of physical storage, the core difference between us and a lot of other people is that we use basically the equivalent of a linked list implementation. So basically, when you want to go from a node to another node, that's a linked list traversal. You don't need to traverse an index in order to get there. And that's why I think even to the other NoSQL guys, we're probably 1,000x faster on graph traversals because it's just one pointer dereference in memory. So that's that part. As for referential integrity, the graph database will ensure that you can't create a relationship to a node that doesn't exist. You can't even delete the node without first deleting its relationships. So we're very strict on that. But, of course, in terms of you can always add data which is inconsistent in terms of adding a property to one thing and forget to add another property or something like that. So that's. Go.
I'd like to point out, I was using Vercent object-oriented database back in 2003, so it's not all started in 2000.
Oh, right. Yeah, that's true. That's true. Yeah, of course. That's true. I think, we did from object-oriented databases in the sense that what they've done is that they've taken a programming paradigm and made a data model out of it, which I think is the wrong way to go about it. I think that the relational guys had it figured out, and they said that we should separate data and logic. I just disagree with them that the fundamental best abstraction for it today is tables. I think that graphs is a better abstraction.
I would agree. I think this is a much better approach because with the full object databases, you would have problems like you would have to have concrete classes, you couldn't declare variables, interfaces, things like that.
Right, and when you upgrade your software, you need to keep that in state. It's a big mess. And you can't look at the data without having access to the classes and all those things. Yeah. All right, great. Thank you, guys.